Hello everyone, this video is about half-wave dipole antenna. And half-wave dipole antenna is similar to Hertzian dipole with the only exception, actually with more exceptions. One of the exceptions is the length of the dipole is much longer. In the case of Hertzian dipole, the length is going to be less than lambda divided by 50. But in the Hertzian dipole, but in the half-wave dipole, the length is comparable to lambda or half lambda. So um, to begin with, we need to uh, declare an assumption. Yeah, the length assumption of the length is comparable to the wavelength. And now the current distribution should be sinusoidal. Yeah. So in this scenario, we have shown the current at the tip of the upper segment is zero. So I V at the upper segment, let's say in this case, yeah, assuming this is zero, and then the top position is plus L divided by 2. And then in the lower bottom, we have the similar arrangement. So minus L divided by 2. So if I V is equal to L divided by 2, then uh, we need to assume that it is 0. And on the other hand, we assume the current to be sinusoidally distributed. The maximum is going to be at the middle. In this case, the current density is going to be sine I know sine k and then uh, L divided by 2 minus Z for the upper segment. So if uh, 0 L divided by 2. And in the lower segment, we have a similar treatment. It will be L divided by 2 plus Z. If um, 0 minus L by 2. So this is the first thing we need to have, the current distribution. And based on this distribution, we will be able to work out the radiation pattern of the whole antenna. And previously, in the previous chapter, we know that in order to find the radiation pattern of the Hertzian dipole antenna, we need to use the method so-called magnetic vector potential. And from here, we know that uh, the magnetic vector potential is given by uh, A V and then mu 4 pi and then L divided by 2 minus L divided by 2, where L here represents the length of the magnetic vector potential, the Hertzian dipole antenna. So I have I and then exponential minus j k r divided by r and d. So this is the way how we can use to establish the uh, magnetic vector potential. From here, we need to use the curl of A to find the magnetic field. And we know that by using the curl of A, we found that the um, magnetic field is going to be J, K, I naught, and then exponential 4 pi r sine theta. And then the length. And similarly, if we want to find the electric field, what we need to do is we just use this, and then we change the direction. The field, the B field here is in the direction of phi, and the electric field here will be in the direction of theta. And this is what we are going, what we got. So according to here, it is J, and then we just put theta here, K I naught. So this is what we can get, what we have got from the last lectures. L and then in the half-wave dipole, we assume that the whole length of antenna consists is a cascade of multiple small segments, multiple Hertzian dipole antenna. So in this case, we have a Hertzian dipole antenna in the position of Z, and the next one will be another Hertzian dipole antenna, and the next one like this. So in other words, each segment along the body of the halfway dipole antenna is actually a Hertzian dipole antenna, and the final length here uh, is a cascade of the arrays of Hertzian dipole antenna. So in other words, based on the result that we have got from the last lectures, um, we if we are going to find the radiation pattern contributed by dz here, we will replace dl with dz, and the electric field over this little segment here will become dz, dz, and then dE. Uh, and the current here is going to be uh, uh, I know, yeah, but actually the current is not the same along the body of the antenna. The current at the tip is minimum, while the current at the midpoint here is maximum. The current distribution is sinusoidal. So in this case, the current here will be replaced with IZ. Uh, so I and then Z. I'm not sure whether you can see the light more clearly. Not quite. So I'm going to rewrite this little bit here. So, so it's going to be R beta and then I Z and then D Z. Uh, so it's almost done. Almost done. A lot yet. Another thing that we need to pay attention to is the direction, okay, um, of the radiation pattern. Right now, we have this current distribution. Suppose the little segment here has a radi has a ray of uh, magnetic field, a ray of radiation field, and angle, the angle here is theta. And the next one, so this is R, and the next one, let's say uh, down here, yeah, it will be more or less parallel because we are looking for the radiation pattern um, from the perspective of far field. The distance R is going to be very large. Uh, so all these lines will be more or less parallel from the microscopic point of view. So we have theta here as well. And if we construct a right angle triangle here, we know what the path difference can be calculated from here. If the length here is Z, uh, then the path difference here is going to be uh, uh, Z cosine theta. So suppose this length here is R small one, okay? And at the tip of the antenna, which is here, the the radiation pattern, the vector is R. So we have R R equals to this longer length one here minus uh, Z cosine theta. So on the other hand, we also need to make up an assumption. R is more or less equal to R. Yeah. So both of them are approximations, but we make the upper expression is uh, more accurate. So now we are going to find the radiation pattern of the whole length of half-wave dipole based on the result we have got here. The length here is little r, but this is not enough. This little r. We are going to calculate the big R here. So what we can do is to rewrite the expression over here. Then we substitute this small r with the value here and see what we can get. So D is Z. And then this expression J and then eta K and then exponential and then J K and then this R will be replaced by this amount. Let's say in this case let's say that we use capital R for each of them just to avoid all the confusion. And now we are going to replace it with the small r. So this one is going to be r minus z cosine theta. And the bottom one, we have shown we are going to use the approximation. And finally, we just need to use sine theta and the IV. And based on the expressions here, we can now sort out which ones will contribute to the electric field, which one is the variable that contribute to the electric field. And like here, K is independent of the electric field. This one, no. So we have this one here. Yeah, because the length here, the height here is different. And this one. Oh. This one is not, because the theta is fixed. So the next step is to just organize the equation a little bit. The E of J is theta, and then K, and then we change the position, this sine theta here. And that is little one. And what we can do is we explain this expression on the fly. This one minus this one, which is J, and then K Z cosine theta. And finally, sine theta and IZ DZ. And then the whole expression is going to be divided by 4 pi small r. Okay, in order to find the electric field, we need to integrate EE. So the total electric field for these radiation patterns, for this half-wave dipole, is going to be the integral of this one, and the integral which in turn can be calculated from the integral of this expression. Uh, Currently, we saw one expression. Anyway, it's not a big deal. And then now we are going to um, minus L divided by L to V. And now it is very clear. Oh, no. Let's see. It is very clear based on what we can get here. Uh, these few expressions is not going to affect the integral. So we can move them on. And 4 pi can be moved out as well. So what we have left here is going to be this one. Yeah, also this one can be moved on as well. I'm not sure whether R should be moved on. Yes, move on. And now it is clear now. Um, it's going to be JKV cos theta. And then the next thing that we are going to do is to substitute this variable for IZ. But right now, the upper segment have different current distribution than the lower segment. What we can do is we split this integral into two. And we can do IZ here, which is equals to I naught and then sine K L is divided L divided by 2 minus V. So this is the column for the upper segment dV. And on the other hand, we can continue with this one. 0 and then minus L divided by 2. So this is almost done now. Um, it's very tricky to deal with this integral because you have an unusual terms here. But we can use the formula, and if we do that, we can uh, apply the formula here. I'm going to write the formula. Uh, say what we are going to do is to integrate CZ and then sine A plus BZ and then DEZ. The um, outcome of this integral is going to be B square plus C square and C sine A plus BZ and then minus B cosine A plus BZ. So this is what we are going to get after the integration. So what we can do is to make use of this formula and we solve the integral here. The solution is quite lengthy, but fortunately, we know that this bracket expression here is actually an array vector, and in this expression, we can actually simplify it. What we can do is we can k sine theta and then so k by the way, both expressions should have I naught, and this I naught can be moved out of the integral. So what we have here is k I naught and then theta. And finally, and then divided by 4 pi r. And then you can just use manual technique or using MATLAB to resolve this integral. The result for this integral is going to be um, um, 2 and then cosine KL over 2 and then cosine theta minus cosine KL over 2 and then divided by K square cosine sine square. So this is the end result of this lengthy derivation, and we can just we can further simplify it. Right? Right now we have a 2 here, and we have 4 pi r squared here, 4 pi r here. So we can do this. Right? We can simplify the expression on the side. And now we can do that. I think it's almost done now. And this k here can be simplified as well. Sure. This will move to K out. Based on the result we have got here, we can safely um, we can say the uh, electric field, the total electric field is going to be this expression uh, plus this times this expression. So uh, to summarize it, the electric field from a half-wave dipole is going to be equal to E, and then we have multiple terms of expression. We have this one here, K I naught, and then uh, theta, and then sine theta, and then J K R, and divided by 2 pi r, and then f theta. And what is f theta? Where f theta is so-called the array factor. The array refers to this array, yeah, segment of Hessian dipole cascade array factor given by this expression cosine and then KL divided by 2 minus and then cosine KL divided by 2 K sine theta. So this is the final result for the electric field radiation pattern. And uh, this F of beta is the array factor. And how about the sine theta? Sine theta here is the phase factor. Sorry, elemental factor. So we can just elaborate a little bit. Sine theta is the elemental factor. So if you have any question, please leave your question to the comments box. We will try to solve your problem if we have time. Right now, we have already done our job. Thank you very much for your attending the video lectures. Bye bye.